Right now, as you're watching this video, time is moving faster for your head than it is for your feet. I'm not speaking metaphorically. I'm not exaggerating. At this very moment, the atoms in your brain are experiencing a different flow of time than the atoms in your toes. The difference is unimaginably small, but it's real, it's measurable, and it's been proven. Your head is aging faster than your feet. Every single second of your life, this is happening. But here's what will truly shatter your understanding of reality. This isn't some exotic phenomenon that only happens in black holes or distant galaxies. This is happening everywhere, all the time, to everyone and everything. The coffee cup on your desk is experiencing time differently at its top than at its bottom. The mountain peaks are racing through time faster than the valleys. And the most disturbing part, there's no such thing as now that applies to your entire body. You don't exist in a single moment. You're spread across time. If this sounds impossible, good, because what I'm about to reveal will overturn everything you thought you knew about the universe. By the end of this video, you'll understand why time isn't what you think it is, why gravity and time are the same thing, and why Einstein called this realization the happiest thought of his life. This isn't philosophy. This is physics. And it's going to blow your mind. Before we dive deeper into this rabbit hole, do me a favor, hit that like button and subscribe to this channel, because what we're about to explore will fundamentally change how you see reality. Also, drop a comment telling me which country you're watching from and what time it is where you are. I'm curious to see how many different nows are experiencing this revelation simultaneously. Because, spoiler alert, those nows aren't as simultaneous as you think. Let's start with what seems like a simple question. What is time? You might say it's what clocks measure. But that just moves the problem. What are clocks actually measuring? You experience time as a flow, a river carrying you from past to future. You remember yesterday. You anticipate tomorrow. This moment right now feels special. It's the present, the only moment that's real. The past is gone. The future hasn't happened yet. This seems obvious, undeniable, fundamental to existence itself. Here's the twist that will start unraveling everything. Physics has no concept of now, none, zero. When Albert Einstein developed his theories, he discovered something that horrified even him. There is no universal present moment, no cosmic now, shared by everyone in the universe. Your now and my now are not the same thing. And this isn't some minor technical detail. This is a fundamental feature of reality. Think of it like this. Imagine you're standing on a train platform, and a train passes by at incredible speed. You see lightning strike the front and back of the train simultaneously. Both strikes happened at the same time, you say. But here's what will blow your mind. A passenger on the train sees something completely different. To them, the front lightning strike happens before the back one, not because of signal delays or optical illusions. Actually, genuinely, in their frame of reference, one happens before the other. Same two events. Different order. Both perspectives equally valid. This is called relativity of simultaneity, and Einstein discovered it in 1905. But this is just the appetizer. The main course is far stranger. Now you might be thinking, okay, but that's just about fast-moving objects. That doesn't affect my daily life. Oh, but it does. See, Einstein realized something profound. If motion affects time, and if gravity feels like motion, then gravity must affect time too. This wasn't just mathematical speculation. This was a genuine prediction that could be tested. And when it was tested, reality turned out to be even stranger than Einstein imagined. Let me give you an example from your own body that makes this concrete. Your heart is about 3 feet lower than your brain. That means it's about 3 feet deeper in Earth's gravitational field. And because of that, time moves slower for your heart than for your brain. Over an average 80-year lifetime, your heart will have experienced about 90 nanoseconds less time than your brain. Your heart is literally younger than your head by a measurable amount. But here's what makes this truly mind-bending. This isn't because gravity is doing something to time. Gravity is the warping of time. They're not separate phenomena. They're the same thing. When you feel gravity pulling you down, what you're actually feeling is time pushing you into the future at different rates for different parts of your body. Gravity is time. Let me paint you a picture that will reframe everything. Imagine time as a landscape, like hills and valleys. In empty space, far from any mass, time flows smoothly, like a flat plane. But when you bring mass into the picture of a planet, a star time becomes warped, like a valley in this landscape. The closer you get to the mass, the deeper into the valley you go, and the slower time flows. This is what we call a gravitational field. But it's not a force field. It's a time field. Think of it like walking through water of different depths. When you're in shallow water, you can move quickly. In deep water, you move slowly. Now imagine that the depth is how slowly time is flowing, and your natural motion through time is constantly pushing you toward regions where time flows slower. That's gravity. You're not being pulled down by Earth. You're being pushed toward slower time. And since slower time is closer to Earth, you accelerate downward. This explains something that puzzled scientists for centuries. Why does everything fall at the same rate? Whether you drop a feather or a bowling ball in a vacuum, they accelerate downward at exactly the same speed. Newton couldn't explain why. He just said, that's how gravity works. But Einstein revealed the deep truth. They fall at the same rate because they're not really falling. They're following the curvature of time itself. And time curves the same way for everything. Here's your first retention hook. And trust me, you'll want to stick around for this. I just told you that gravity is the warping of time, but that's only half the story. What I'm about to reveal in the next section will show you that space is warped too, and the way space and time warp together creates something so bizarre that when Einstein first realized it, he thought he'd made a mistake. He spent weeks trying to prove himself wrong. He couldn't. Reality was stranger than even he wanted to believe. Let's talk about what Einstein actually discovered. In 1907, 2 years after his miraculous year, when he published the theory of special relativity, Einstein was working at the patent office in Bern, Switzerland. He was thinking about gravity, and he had what he later called the happiest thought of my life. He imagined a man falling off a roof, and he realized something profound. While falling, the man wouldn't feel his own weight. He would feel weightless. This seems obvious now because we've seen astronauts floating in space. But Einstein realized something deeper. If you're in a windowless box and you feel weightless, there's no experiment you can do to determine whether you're floating in deep space, far from any gravity, or whether you're falling freely in a gravitational field. They're identical. This is called the equivalence principle, and it's one of the most important ideas in physics. But here's the kicker. If falling freely in gravity is the same as floating in empty space, then gravity isn't a force at all. When you're standing on the ground, you feel weight, not because Earth is pulling you down, but because the ground is pushing you up. You're being accelerated upward by the ground, and you interpret this as weight. But in reality, your natural motion is to float freely, following the curvature of spacetime, and the ground is interfering with that natural motion. This is going to sound insane, but follow me here. You, right now, sitting or standing while watching this video, are being accelerated upward at 9.8 meters per second squared. You're like someone in an elevator that's accelerating upward in empty space. The floor is pushing you up. That's what you feel as weight. If the ground suddenly disappeared, you wouldn't fall down. You'd finally be able to follow your natural path through curved spacetime. Einstein spent the next 8 years working out the mathematics of this idea. It was brutally difficult. He later said these were the hardest years of his life. He had to learn entirely new branches of mathematics, differential geometry, tensor calculus fields that mathematicians had developed for pure theoretical reasons, never imagining they described the actual structure of the universe. In 1915, Einstein finally published his complete theory, general relativity. The core equation of general relativity is deceptively simple-looking, but contains universes of meaning. It says, the curvature of spacetime equals the distribution of mass and energy, with some constants thrown in. But what this really means is profound. Matter tells spacetime how to curve, and spacetime tells matter how to move. It's a feedback loop. Mass creates curvature, and curvature affects how mass moves, which changes the curvature, which affects the motion, on and on. But let me give you the piece that will truly blow your mind. Einstein's equations showed that time and space aren't separate things that can be warped independently. They're woven together into a single fabric called spacetime. When gravity warps time, it must also warp space. They're inseparable. And the way they warp together is what creates all the bizarre effects we're going to explore. Here's a concrete example: GPS satellites. Those satellites orbit about 12,500 miles above Earth's surface. Up there, they're in a weaker gravitational field than we are on the surface, so time flows faster for them. How much faster? About 45 microseconds per day faster. That might not sound like much, but GPS works by measuring the time it takes for signals to travel from satellites to your phone. Those signals travel at the speed of light, 186,000 miles per second. In 45 microseconds, light travels about 8 miles. So if we didn't account for gravitational time dilation, every GPS device would accumulate errors of about 8 miles per day. Within hours, GPS would be completely useless. But we do account for it. The engineers who designed GPS had to program the satellites to tick their clocks slower to compensate for the faster flow of time they experience. Every time you use GPS to navigate, you're relying on Einstein's theory of gravity as warped time. The fact that GPS works is proof that gravity slows down time. But wait, there's another effect too. Those satellites are also moving fast about 8,700 miles per hour relative to Earth's surface. And according to special relativity, moving clocks tick slower. This effect runs in the opposite direction. It makes the satellite clocks run slow by about 7 microseconds per day. So the total effect is about 38 microseconds per day fast. The engineers account for both effects. They have to. Einstein's predictions aren't optional. They're how reality works. Now here's what makes this truly profound. These aren't small corrections to Newtonian physics. If Einstein was only slightly more correct than Newton, GPS might work, but be slightly inaccurate. But that's not what happens. If you try to build GPS using only Newton's physics, it doesn't work at all. Not approximately, not kind of. It fails completely and rapidly. Einstein isn't refining Newton. He's describing a fundamentally different universe. Think of it like this. Newton thought gravity was a force, an invisible pulling that reaches across space instantaneously. Einstein showed that gravity is the shape of space-time itself, and changes in that shape propagate at the speed of light. These aren't two descriptions of the same thing with different levels of precision. They're completely different ontologies, different stories about what reality is made of. And Einstein's story is the correct one. Let me give you another example that proves time slows down in gravity. The Pound-Rebka experiment. In 1959, physicists Robert Pound and Glenn Rebka did something remarkably clever at Harvard University. They put a gamma-ray emitter in the basement of a building and a detector at the top, 74 feet higher. Then they measured the frequency of gamma rays traveling up versus gamma rays traveling down. Here's what they found. Gamma rays traveling upward, climbing out of Earth's gravitational field, were redshifted, their frequency decreased. Gamma rays traveling downward falling into the gravitational field where blue shifted. Their frequency increased. This is exactly what Einstein predicted. The gamma rays themselves are tiny clocks, oscillating at a particular frequency. As they climb up to where time flows faster, they appear to tick slower. As they fall down to where time flows slower, they appear to tick faster. The measurement matched Einstein's prediction to within 1% accuracy. But here's the beautiful part. Pound and Rebka measured this over a height difference of just 74 feet. That's a trivial distance, cosmically speaking. Yet even over that tiny distance, the effect was measurable. This tells us something crucial. Gravitational time dilation isn't some exotic effect that only matters near black holes. It's happening everywhere, all the time, at every scale. It's fundamental to how the universe works. Now, I know what you're thinking. This is fascinating, but what does it really mean? What is time, actually? And that's the perfect question, because what I'm about to reveal will show you that time isn't what you think it is. Time isn't a river. It isn't a dimension like space. It's something far stranger. And understanding what time really is will unlock the deepest secrets of gravity. Stay with me, because we're about to go deep. Let's confront something head-on. What is time, really? Not what it does, we know it flows. We experience it passing. But what is it fundamentally? Is it a thing? An illusion? A dimension? This question has haunted physicists and philosophers for centuries. And the answer that modern physics has arrived at is going to disturb you. Time might not exist at all, at least not in the way you think it does. Here's what I mean. In physics, we describe the world using something called a state. At any given moment, every particle has a position, a velocity, certain properties. The state is the complete description of all of these properties for every particle in the system you're studying. And time, in physics, is just a parameter that tells us how the state changes. It's like the page numbers in a book. The story exists, all the pages are there, but the page numbers help you read it in order. But here's the disturbing part. In Einstein's general relativity, there's a serious problem with this picture. When you include gravity, when space-time itself can be curved and dynamic, the whole notion of time as a universal parameter breaks down. Different observers experience different flows of time. There's no objective fact about what's happening now across the universe. The page numbers of the book become ambiguous, observer-dependent. Some physicists have taken this to its logical conclusion and argued that time doesn't fundamentally exist. The universe, in this view, just is a timeless, four-dimensional block of space-time containing everything that ever was, is, or will be. The flow of time is an illusion created by our consciousness moving through this block. Like reading a book page by page, even though all the pages already exist. This is called the block universe or eternalism, and it has profound implications. If it's true, then the past still exists. It's not gone. It's just in a different region of space-time. And the future already exists too. It's not yet to come. It's already there, waiting for you to experience it. Your entire life, from birth to death, exists as a four-dimensional structure in space-time, and your consciousness is simply moving along it, creating the illusion of time flowing. Think of it like this. Imagine a movie. All the frames exist simultaneously on the film. But when you watch the movie, you experience them one at a time, in sequence, creating the illusion of motion and change. In the block universe view, space-time is the film, and your consciousness is the projector, moving through it frame by frame, creating the illusion of time flowing. But here's what will blow your mind. If the block universe is correct, then nothing ever changes. Change is an illusion. What we call change is just different configurations existing at different temporal locations, the same way different objects exist at different spatial locations. A tree doesn't change from young to old. There's a young tree at one time location and an old tree at another time location, both equally real, both eternally existing. This has staggering implications for free will, for the nature of reality, for what it means to be alive. If the future already exists, is it predetermined? Do you have any choice in what you'll do? Or are you simply experiencing a story that's already been written? This is where physics crashes into philosophy, and the answers aren't clear. But let's bring this back to gravity. If time is relative, if it flows at different rates in different places, what does that tell us about the nature of reality? Here's the crucial insight. It tells us that spacetime isn't a stage where physics happens. Spacetime is a physical thing itself. It can bend, warp, ripple. It's as real as matter and energy. Maybe more real, because matter and energy are just patterns of curvature in spacetime. Einstein's equations tell us exactly how spacetime curves. The amount of curvature depends on the amount of mass and energy present. More mass means more curvature. And more curvature means slower time. Let me make this concrete with actual numbers. At sea level on Earth, time flows at a certain rate. Let's call that 1.0 seconds per second normal time. If you climb a mountain, let's say Mount Everest, you're now about 5.5 miles higher. You're slightly farther from Earth's center, so you're in a slightly weaker gravitational field. How much faster does time flow at the top of Everest? The effect is tiny, about 30 microseconds faster per year compared to sea level. Over a human lifetime of 80 years, someone living on top of Everest would age about 2.4 milliseconds more than someone at sea level. You wouldn't notice it, but it's real. It's been measured, and it's happening. But let's go to an extreme example, a neutron star. Neutron stars are the crushed cores of dead massive stars. They pack about 1.4 times the mass of our sun into a sphere only about 12 miles across. The gravity is so intense that on the surface of a neutron star, time runs about 30% slower than it does far from the star. If you could somehow stand on a neutron star for what felt like 10 seconds to you, about 14 seconds would pass for someone far away. The difference is enormous. And if you go even more extreme, to the edge of a black hole, time dilation becomes infinite. At the event horizon, the boundary of a black hole, time from an outside perspective stops completely. If you watch someone fall into a black hole, you would never see them cross the horizon. You'd see them get slower and slower, more and more redshifted, fading and freezing at the edge. From your perspective, they take infinite time to fall in. But from their perspective, they cross the horizon in finite time and continue falling to the center. Same event. Radically different experiences. This is the power and the strangeness of general relativity. Time isn't absolute. It's not a universal river carrying everything along together. It's local, personal, dependent on where you are and how fast you're moving. And this means something profound. There is no objective truth about the order of events across space. If two things happen far apart, different observers can legitimately disagree about which happened first. Let me give you a thought experiment that will crystallize this. Imagine two events. A supernova explodes in a distant galaxy, and at the same time, you snap your fingers here on Earth. Did the supernova happen before, after, or simultaneously with your finger snap? The shocking answer is, it depends who you ask. An observer moving relative to you at high speed could see the supernova before your snap, or after your snap, or simultaneously. All three are equally valid. There's no fact of the matter about which really happened first. This destroys our intuitive notion of causality. We think cause must precede effect. But if the order of events is observer-dependent, how can we even define causality? Einstein's answer is brilliant. Events can only causally affect each other if they're close enough in spacetime that light could travel between them. If two events are so far apart that light couldn't travel from one to the other, then they can't causally influence each other, and their order can be observer-dependent. This preserves causality while allowing the relativity of simultaneity. But here's the truly mind-bending implication. This means the universe doesn't have a single history. Different observers, moving at different speeds, slicing through space-time at different angles, will decompose reality into different sequences of events. They're all looking at the same space-time, but they're slicing it differently into space and time. It's like how you can slice a loaf of bread straight across or at an angle. You get different slices, but it's the same loaf. Now, I promised you a revelation that would reframe everything, and here it is. Gravity doesn't just slow down time. Gravity is time. More precisely, what we experience as gravity is the consequence of time flowing at different rates at different positions. Let me explain what I mean. Imagine you're standing still. Even though you're not moving through space, you are moving through time 1 second per second, moving into the future. That motion through time is real, physical motion through space-time. Now, here's the key. In curved space-time, the direction of future is different at your head than at your feet. Your feet are deeper in the gravitational field, where time flows slower. Your head is higher up, where time flows faster. Both parts of you are trying to move into the future, but the future points in slightly different directions. This creates a twist, a tension in your body, and that tension is what you feel as weight. Gravity is the feeling of different parts of your body trying to move through time in different directions. This is why everything falls at the same rate. It's not that gravity pulls harder on heavier objects. It's that all objects are following the same curvature of space-time, the same gradient of time flow. A feather and a bowling ball fall at the same rate because they're both following paths of least resistance through curved space-time. And those paths are determined by the curvature, not by the properties of the objects. Here's your second major retention hook. Everything I've told you so far explains how gravity slows down time. But it doesn't explain why. Why should mass curve space-time? Why should time slow down near massive objects? The answer to this question involves quantum mechanics, and it's going to take us into territory so strange that even Einstein refused to accept it. He called it spooky action at a distance, and spent the last decades of his life trying to prove it was wrong. He failed. The universe really is that weird. Stay with me, because what comes next will change everything you thought you knew about reality. Let's pivot to something that seems completely different, but will turn out to be deeply connected: quantum mechanics. You've probably heard that quantum mechanics is weird. Particles can be in two places at once. They're waves and particles simultaneously. Observation affects reality. All of this is true, but it's weirder than you've been told. And when we combine quantum mechanics with gravity, we get insights that are almost unbearably strange. Here's the basic strangeness of quantum mechanics. At the smallest scales, reality is fundamentally probabilistic. An electron doesn't have a definite position until you measure it. Before measurement, it exists in a superposition, a quantum state that's a combination of being in multiple places simultaneously. When you measure it, the superposition collapses and the electron appears in one place. But before measurement, it genuinely doesn't have a position. This isn't ignorance on our part. It's fundamental to how reality works. This was discovered in the 1920s by physicists like Werner Heisenberg, Erwin Schrödinger, and Niels Bohr. Einstein hated it. He famously said, "God does not play dice with the universe." He believed there must be hidden variables, deeper deterministic laws that we just haven't discovered yet. But experiments over the past century have proven Einstein wrong on this point. The universe really is probabilistic at its core. Reality genuinely doesn't have definite properties until you measure them. But here's where it connects to gravity. Time is part of reality. So if reality is fundamentally quantum, time must be quantum too. But what does it mean for time to be quantum? This is one of the deepest unsolved problems in physics. We have quantum mechanics, which describes the behavior of particles and fields. We have general relativity, which describes gravity as the curvature of spacetime. But we don't have a quantum theory of gravity. We don't know how to make general relativity and quantum mechanics work together. This might seem like a technical problem for physicists to solve, but it has profound implications for reality. Here's why. Quantum mechanics requires time to be a fixed background, a stage on which quantum events unfold. But general relativity says time is dynamic, changing, part of the physical system. These requirements are contradictory. Something's got to give. Either quantum mechanics needs to be modified, or general relativity does, or both do. We don't know which, but we have clues. One comes from black holes. In 1974, Stephen Hawking made an astonishing discovery using quantum field theory in curved spacetime. He found that black holes aren't completely black. They emit radiation, now called Hawking radiation. This happens because of quantum effects near the event horizon. Virtual particle pairs pop into existence everywhere in space, normally annihilating each other immediately. But near a black hole's horizon, one particle can fall in while the other escapes. The escaped particle becomes real, carrying energy away from the black hole. This means black holes evaporate. Slowly, incredibly slowly, but inevitably. A black hole with the mass of our Sun would take about 1,067 years to evaporate completely far, longer than the current age of the universe. But the implication is profound. Black holes are not eternal. They have entropy. They have temperature. They're thermodynamic objects. And this connects gravity to thermodynamics in ways we're still trying to understand. Here's where it gets truly mind-bending. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This is bizarre. Normally, entropy scales with volume. The more stuff you have, the more entropy. But for black holes, it scales with surface area. This suggests something radical. All the information about what's inside a black hole might be encoded on its surface. The three-dimensional interior might be a projection of information stored on the two-dimensional surface. This idea, called the holographic principle, has been extended by some physicists to the entire universe. Maybe our three-dimensional reality is actually a holographic projection of information encoded on a distant two-dimensional surface. If true, this would mean that everything you see, everything you experience, including the flow of time and the pull of gravity, is a kind of illusion, a shadow, cast by more fundamental processes happening in a lower dimensional space. Now, I know this sounds like science fiction, but it's serious theoretical physics, developed by people like Gerard 't Hooft and Leonard Susskind in the 1990s, and there's mathematical evidence supporting it. In certain theoretical models, physicists have shown that a quantum gravity theory in a space with a certain number of dimensions is mathematically equivalent to a non-gravitational quantum theory on the boundary of that space, with one less dimension. Gravity emerges from the boundary theory. It's not fundamental, it's derived. Let me bring this back to our main question. Why does gravity slow down time? In the holographic picture, gravity and time aren't fundamental features of reality. They're emergent phenomena, patterns that appear when you look at the universe from a particular perspective. The fundamental reality might be something utterly different, quantum information encoded on distant surfaces, obeying laws that have nothing to do with space, time, or gravity as we know them. But we can go even deeper. Let's talk about the connection between time and entropy. Entropy is a measure of disorder, of how spread out and randomized energy becomes. The second law of thermodynamics says entropy always increases. This is why you can scramble an egg, but not unscramble it. Why coffee and milk mix, but never spontaneously separate. Why time seems to flow in one direction. But here's the thing. The fundamental laws of physics are time-symmetric. They work the same forwards and backwards in time. If you watch a video of planets orbiting or particles colliding and play it backwards, it still looks like it obeys the laws of physics. So why does time have a direction? Why do we remember the past but not the future? Why does entropy increase? This is called the arrow of time, and it's one of the deepest mysteries in physics. The answer seems to involve the Big Bang. At the beginning of the universe, for reasons we don't understand, entropy was extremely low. The universe was in a highly ordered state. Since then, entropy has been increasing, disorder spreading, and that increase creates the arrow of time. Time flows from past to future, because that's the direction of increasing entropy. Memory works in one direction, because recording a memory is a process that increases entropy. But here's the connection to gravity. Gravity tends to clump matter together. Stars form, galaxies form, planets form. This seems like increasing order, decreasing entropy. But actually, gravitational clumping increases entropy because it converts potential energy into heat and radiation. When a cloud of gas collapses to form a star, the star heats up and radiates energy into space. That radiated energy is more disordered than the original cloud. Entropy increases. And here's the profound part. Time flows because entropy increases, and entropy increases partly because of gravity. Gravity, by clumping matter and creating time dilation around massive objects, plays a role in creating the arrow of time. The flow of time and the pull of gravity are intimately connected, not just geometrically through space-time curvature, but thermodynamically through the increase of entropy. Think of it like this. The universe is like a movie that started highly ordered and is gradually becoming more disordered. Gravity writes the plot of that movie by determining where matter goes, how stars and galaxies form, how black holes create the ultimate disorder. And time is the experience of watching that movie unfold, frame by frame, from order to disorder. Now here's something that will truly blow your mind. Some physicists believe that time might not be fundamental at all. Instead, time might emerge from quantum entanglement. Entanglement is a phenomenon where quantum particles become correlated in ways that can't be explained by classical physics. Measure one particle, and you instantly know something about another particle, even if they're light years apart. Einstein called this spooky action at a distance and thought it proved quantum mechanics was incomplete. But experiments have proven entanglement is real, and some recent work suggests that the geometry of space, and possibly the flow of time, emerge from the pattern of quantum entanglement between particles. In this view, space and time aren't fundamental. What's fundamental is the quantum information and the correlations between bits of that information. Space and time are how those correlations manifest to observers like us. If this is correct, and it's speculative, cutting-edge stuff, then gravity slows down time because gravity is a manifestation of how quantum entanglement is distributed in the universe. More mass means more entanglement, which means more space-time curvature, which means slower time. Gravity doesn't slow down time. Gravity is the pattern of quantum entanglement that we perceive as time slowing down. I know this is abstract and mind-bending. Let me give you something concrete to anchor it. In 2010, physicists at the National Institute of Standards and Technology in Boulder, Colorado, built the most accurate clocks ever created, atomic clocks accurate to 1 second in 3.7 billion years. And they used these clocks to measure gravitational time dilation over the smallest distance ever, just 1 foot. They put one clock a foot higher than the other and measured the difference in their tick rates. The result? The higher clock ticked faster by a few parts in 1016. To put that in perspective, over a human lifetime of 80 years, the higher clock would gain about 90 nanoseconds, 90 billionths of a second. But they measured it over just hours. This is how precise modern technology has become. We can measure time dilation over the height of a single step. Gravity's effect on time isn't theoretical. It's measurable in your house right now with the right equipment. What this tells us is that the effects we're talking about aren't exotic phenomena that only matter in extreme situations. They're fundamental to how reality works, at every scale, in every situation. Your body, your house, your life, all of it exists across a gradient of time. Different parts of you experience time flowing at different rates. This is just how the universe is. And the fact that you don't notice it, that it seems counterintuitive, only shows how limited our evolutionary intuitions are. We evolved to throw spears and find fruit, not to intuit the structure of spacetime. Now, before we go deeper into the implications of all this, let me give you another retention hook. Everything I've told you explains how gravity relates to time from a physics perspective. But I haven't yet told you the truly disturbing part. How this affects your personal experience of reality, your sense of self, your understanding of consciousness. Because if different parts of your body exist at different moments in time, what does that mean for your consciousness? Are you a single unified being, or a collection of slightly out-of-sync processes? The answer will disturb you. Stay with me. Now let's talk about something that will bring all of this into sharp personal focus. What does gravitational time dilation mean for you as a conscious being? You've learned that time flows at different rates in different gravitational fields, that your head ages faster than your feet, that there's no universal now. But what does this mean for your conscious experience? Are you really experiencing a single moment, or are you spread across time? Here's where things get philosophically deep. Consciousness feels unified. You experience a single now, a single moment of awareness that encompasses your entire body and mind. But physics tells us this is an illusion. Different neurons in your brain are experiencing slightly different moments. Your brain at the top of your head is fractionally ahead in time compared to neurons at the base of your skull. The difference is unimaginably tiny nanoseconds, but it's real. So why does consciousness feel unified? This is one of the deepest mysteries in neuroscience and philosophy of mind. The leading theory is that consciousness doesn't emerge from any single moment. Instead, it emerges from patterns of information processing that take time to unfold. Your experience of now is actually a brief window, roughly 100 milliseconds long, during which your brain integrates information from different senses and different brain regions into a coherent experience. But here's what makes this truly bizarre. That integration process itself takes time. And during that time, gravitational time dilation is affecting different parts of your brain differently. Your conscious experience is being stitched together from moments that aren't quite simultaneous. You are, in a very real sense, experiencing multiple moments at once, averaged together into the illusion of a single now. Think of it like watching a movie. Each frame is slightly different, captured at a slightly different moment. But when played at 24 frames per second, your brain blends them into smooth motion. You don't see 24 separate images, you see continuous flow. Similarly, your consciousness blends the slightly out-of-sync signals from different parts of your body and brain into what feels like a single unified moment. But that unity is constructed, not fundamental. This has profound implications for the concept of free will. When you make a decision, different parts of your brain are involved in processing that decision at slightly different times due to gravitational time dilation. Now, the difference is infinitesimal, far too small to matter practically. But conceptually, it raises a question. Which moment is the real moment of decision? Is there even such a thing as a single moment when you choose? Neuroscience has already complicated free will without even considering relativity. Experiments by Benjamin Libet in the 1980s showed that brain activity associated with a decision begins about 300 milliseconds before you become consciously aware of making that decision. Your brain decides before you consciously decide. But add gravitational time dilation to the mix, and it gets even stranger. Different observers in different gravitational fields or moving at different speeds would disagree about when your decision happened. The timing of your choice is relative. But let's step back from these philosophical depths and look at something more concrete: how gravitational time dilation has been verified again and again through increasingly precise experiments. In 2010, we mentioned the experiment that measured time dilation over 1 foot. But in 2022, physicists took this even further. They used quantum entanglement to measure gravitational effects on time at the millimeter scale smaller than the width of your fingernail. The experiment, conducted by researchers at the University of Vienna, used entangled photons and showed that quantum coherence, the delicate property that makes quantum computers possible, is affected by gravitational time dilation. They found that photons traveling through different gravitational potentials experienced different amounts of time, and this affected their quantum properties in exactly the way Einstein's theory predicted. Gravity isn't just warping spacetime at large scales. It's affecting the fundamental quantum nature of reality at the smallest scales. Here's another astonishing verification: gravitational redshift in the Sun. In 1959, the same year as the Pound-Rebka experiment on Earth, physicists were analyzing light from the Sun. Light emitted from the Sun's surface has to climb out of the Sun's gravitational field to reach us. Because time runs slower on the Sun's surface than in empty space, and because the frequency of light is a kind of clock, light from the Sun is gravitationally redshifted. Its wavelength is stretched, its color shifted toward red. The amount of redshift depends on the mass and radius of the Sun, exactly as Einstein's equations predict. By measuring this redshift precisely, physicists confirmed that time runs about 2 parts per million slower on the Sun's surface than far from the Sun. For every million seconds that pass far from the Sun, about 11.5 days, only 999,998 seconds pass on the Sun's surface. The difference seems tiny, but it's measurable, confirmable, and it proves the theory. But let's go to the extreme. What happens near a black hole? This is where gravitational time dilation becomes not just measurable, but dominant, traumatic, reality warping. Near the event horizon of a black hole, time slows down so much that from an outside perspective, it appears to stop completely. If you watched an astronaut fall toward a black hole, here's what you'd see. They'd appear to slow down as they approached the horizon. Their movements would become sluggish, then glacial, then frozen. Light from them would be increasingly redshifted, making them appear dimmer and redder. Eventually, they'd fade from view, frozen at the edge of the horizon forever from your perspective. You would never, even waiting infinite time, see them cross the horizon. But from the astronaut's perspective, something completely different happens. They feel nothing special at the horizon. They cross it in finite time seconds or minutes, depending on the black hole's size. They don't even know when they've crossed it. And then they continue falling inward, toward the singularity at the center, where space-time curvature becomes infinite and general relativity breaks down. This is called the observer dependence of black hole physics, and it's one of the most disturbing features of general relativity. The same event, the astronaut crossing the horizon, takes infinite time for you, but finite time for them. Both perspectives are equally valid. There's no objective fact about when or whether the crossing happens. Reality itself is observer dependent. But here's something even stranger that will truly blow your mind. Inside the event horizon, space and time swap roles. Outside the horizon, you can move freely through space, but are dragged inexorably forward in time. Inside the horizon, you can move freely through time, but are dragged inexorably toward the singularity in what used to be space. The future literally becomes a place, the center of the black hole. You can't avoid going there any more than you can avoid going into the future outside the horizon. This spatial temporal role reversal shows just how intimately connected space and time really are. They're not separate things that happen to interact. They're two aspects of a unified entity spacetime, and which aspect is space and which is time depends on the curvature, on how strong the gravitational field is. Now let me tell you about one of the most mind-blowing confirmed predictions of general relativity: gravitational waves. Einstein predicted in 1916 that when massive objects accelerate like two black holes, orbiting each other, they should create ripples in spacetime itself, waves of curvature that propagate at the speed of light. But these waves would be incredibly weak, and Einstein himself doubted they could ever be detected. For decades, gravitational waves remained a theoretical curiosity. But in the 1970s, physicists Russell Hulse and Roy Taylor discovered a binary pulsar-2 neutron stars orbiting each other. They observed this system for years and found that the orbit was decaying, shrinking exactly as predicted if the system was losing energy by radiating gravitational waves. This was indirect evidence for gravitational waves and earned them the Nobel Prize in 1993, but direct detection came later. In 2015, the LIGO experiment, two enormous L-shaped detectors in Louisiana and Washington state, detected gravitational waves directly for the first time. The signal came from two black holes, each about 30 times the mass of the Sun, that had spiraled into each other and merged 1.3 billion years ago. The collision released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that moment. When these waves passed through Earth, they compressed and stretched spacetime itself. The LIGO detectors, with arms 2.5 miles long, measured changes in length smaller than 1,000th the width of a proton. They detected spacetime itself vibrating, and the signal matched Einstein's predictions, exactly the chirp of two black holes merging, encoded in the warping of spacetime. Since then, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events. In 2017, they detected the collision of two neutron stars, and within seconds, telescopes around the world turned to observe the same event in light, gamma rays, X-rays, and radio waves. It was the most observed astronomical event in history, and it confirmed not just that gravitational waves exist, but that they travel at the speed of light, just as Einstein predicted. But here's what this means for time. Gravitational waves are waves of time dilation. As they pass through you, time speeds up and slows down in an oscillating pattern. Your head and feet experience different flows of time in a rhythmic pattern. The effect is tiny even from those merging black holes. The time dilation was less than 1/10000000th of a second. But it's real. When gravitational waves wash over Earth, they're literally making time wobble. Now, let's connect this to something personal: aging. You age because time passes for you. But we now know that time passes at different rates, depending on your gravitational environment. So people at different elevations age at different rates. This has been confirmed experimentally. In the 1970s, physicists Joseph Haffel and Richard Keating flew atomic clocks around the world on commercial airplanes and compared them to clocks that stayed on the ground. The flying clocks, being higher up and in a weaker gravitational field, ticked faster. But they were also moving fast, which made them tick slower due to special relativity. The combined effect was small but measurable. The flying clocks gained about 273 nanoseconds compared to the ground clocks, once both gravitational and velocity effects were accounted for. The experiment confirmed both special and general relativity simultaneously. But think about what this means. Airline pilots, flight attendants, frequent flyers, they're all aging slightly faster than people who stay on the ground. Over a career of flying, a pilot might age a few microseconds more than their earthbound twin. The effect is absurdly tiny, but it's real, and it scales up. Astronauts on the International Space Station are in an even weaker gravitational field, so they age even faster. Over a year in space, an astronaut ages about 0.007 seconds more than people on Earth. Conversely, people living in deep valleys or basements are deeper in Earth's gravitational field and age slightly slower. If you wanted to maximize your lifespan measured in your own time, you'd live as deep underground as possible. But of course, less time passes for you, so you wouldn't actually experience more. You'd just be out of sync with the rest of the world. This leads to a philosophical question. What does it mean to age? Is it about how much time you experience, or about how much time passes in the universe? These sound like the same thing, but relativity shows they're not. You could live deep in a gravitational well, experience 80 years of subjective time, but emerge to find that 100 years have passed in the outside world. Did you age 80 years or 100 years? The answer depends on what you care about. If you care about subjective experience, you aged 80 years. You experienced 80 years of consciousness, memories, thoughts. But if you care about your relationship to the rest of the universe, you aged 100 years. Your friends are gone. The world has changed. You're out of sync. This isn't just philosophical speculation. It's a real issue for any future long-distance space travel. If humans ever travel to nearby stars at relativistic speeds, significant fractions of the speed of light-time dilation will become extreme. An astronaut might experience a 10-year journey, but return to find that 100 years have passed on Earth. They'd be meeting their great-great-grandchildren, who are older than them. Everyone they knew would be dead or ancient. This is called the twin paradox, though it's not really a paradox. It's just a counterintuitive consequence of relativity. If one twin travels at high speed and returns, they'll be younger than the twin who stayed home. It's been verified experimentally with atomic clocks on airplanes and with particles in accelerators. It's as real as gravity itself. Here's your third retention oak. Everything I've told you shows how gravity slows down time and how this has been confirmed through countless experiments. But I still haven't told you the most disturbing implication, how this destroys the concept of now and what that means for consciousness, memory, and identity. If there's no universal present moment, then what are you? When are you? The answer will shake your understanding of existence itself. Stay with me, because we're about to explore the deepest implications of relativity for human experience. Let's confront something that will fundamentally challenge your sense of reality. The destruction of now. You experience the present moment as special, as uniquely real. The past is gone, just memories. The future hasn't happened yet, just possibilities. But right now, this moment is real. You're experiencing it. This seems undeniable, more certain than anything else. But physics says you're wrong. There is no universal now, no cosmic present moment shared by everyone in the universe. This isn't speculation or interpretation. It's a direct consequence of Einstein's relativity, confirmed by every experiment ever done. And the implications are staggering. Here's why there's no universal now. Simultaneity is relative. Whether two events happen at the same time depends on your motion and your gravitational environment. An event that's happening right now for you might have happened in the past or future for someone moving relative to you. And both perspectives are equally valid. There's no objective fact about what's happening now across the universe. Let me make this concrete with a thought experiment called the Andromeda paradox, devised by physicist Roger Penrose. Imagine two people walking past each other on the street, one heading north and one heading south, each moving at a gentle walking pace of about 3 miles per hour. They're on Earth, and there's the Andromeda galaxy, 2.5 million light years away. Due to the relativity of simultaneity, what's happening now in Andromeda is different for these two walkers. For the person walking away from Andromeda, the current moment in Andromeda might be a day in what would be their future if they were stationary. For the person walking toward Andromeda, the current moment might be a day in what would be their past. Just by walking at different speeds, these two people have shifted what's happening now in Andromeda by about a week relative to each other. Both are correct. Both are seeing genuine simultaneity from their reference frame. But they disagree by a week about what's currently happening in a distant galaxy. This means that now isn't a property of the universe. It's a property of observers. The present moment is subjective. But here's where it gets truly disturbing. If there's no universal now, then the past and future don't have objective boundaries either. Events you think of as past might still be in the present for someone else. Events you think of as future might already be in the past for someone else. The whole notion of past, present, and future becomes scrambled, observer-dependent, subjective. This leads to the block universe interpretation I mentioned earlier, but now you can understand it more deeply. If all moments in time are equally real, and now is just a subjective label we apply to our current experience, then all of time exists simultaneously. The Big Bang is still happening. It's just at one end of space-time. The heat death of the universe is already there at the other end. Your birth, your death, every moment of your life all exist eternally in the four-dimensional structure of space-time. You might object, but I experience time flowing. I feel myself moving from past to future. Yes, you do. But that experience doesn't mean time is actually flowing. It just means you have memories of earlier states and not later ones. Your consciousness moves along your world line, your path through space-time, creating the illusion of flow. But the world line itself is static, eternal, unchanging. Think of it like a movie film again. All the frames exist simultaneously on the reel. But when you watch the movie, you experience them in sequence. Your consciousness is like a projector beam, illuminating one frame at a time, creating the experience of motion and change. But the motion is in your experience, not in the film itself. This view has profound implications. If the block universe is correct, then everything that will ever happen to you has already happened, in a sense. It exists in space-time, frozen, eternal. You're not moving through time toward an open future. You're following a path that already exists, and your experience of choosing and deciding is part of that path, not something that creates it. Does this eliminate free will? That's one of the most controversial questions in philosophy. Some argue yes, if the future already exists, then it's determined, and you can't change it. Others argue, no, you still make choices, and those choices are part of the causal structure of space-time. The future exists, but it exists because of your choices, not despite them. Your choices are part of what creates the block universe. I lean toward the second view, but I'll be honest, this is where physics gives way to philosophy, and there's no consensus. Different physicists and philosophers interpret the block universe differently. Some embrace it fully. Others reject it, arguing for alternative interpretations of relativity. Still others think the question is meaningless, that we're asking about something that doesn't have an answer. But regardless of interpretation, the observational facts remain. Time flows at different rates in different places. There's no universal simultaneity, and the order of events can be observer-dependent. These aren't philosophical positions. They're experimental facts, and they force us to reconsider what time is and what it means to exist in time. Now let's talk about something related, but even stranger: the connection between gravity, time, and information. In recent decades, physicists have increasingly come to view information as fundamental to reality. Not matter, not energy, but information, the patterns, the structure, the correlations that define what's what and where's where. This view was crystallized by the physicist John Wheeler, who coined the phrase "it from bit," suggesting that every physical thing, it, derives from information, bit. In this view, reality is fundamentally about information processing, and matter and energy are patterns of information. But what does this have to do with gravity and time? Here's the connection. Gravity seems to be deeply related to entropy, and entropy is a measure of information, specifically missing information. The more entropy a system has, the less you know about its detailed microscopic state. And the connection between gravity and entropy suggests that gravity itself might be an emergent phenomenon arising from information theory. This idea was developed by physicist Eric Verlinde in 2010 in a controversial paper called Entropic Gravity. Verlinde argued that gravity isn't a fundamental force at all. Instead, it emerges from the statistical behavior of information encoded on surfaces. When matter moves, it changes the distribution of information, and this change creates what we perceive as gravitational attraction. The idea is still controversial and hasn't been fully proven, but it has some compelling features. It explains why gravity seems different from other forces, why it's always attractive, why it couples to all forms of energy equally, why it's so much weaker than other forces. According to Verlinde, these features arise naturally if gravity is emergent rather than fundamental. And if gravity is emergent from information theory, then time dilation, the slowing of time in gravitational fields, might also be emergent. Time might not be a fundamental feature of reality, but rather a statistical phenomenon that emerges from the behavior of vast numbers of information processing elements. This connects to the holographic principle I mentioned earlier. If information is fundamental, and if all the information about a region of space can be encoded on its boundary, then the interior, including its time evolution, is in some sense a projection of that boundary information. Time becomes a way of organizing information rather than a fundamental dimension. Now, I know this is abstract, so let me ground it with an example: the information paradox of black holes. When matter falls into a black hole, it carries information, the information about its quantum state, its properties, its history. According to general relativity, that information crosses the event horizon and is lost forever, eventually destroyed in the singularity. But according to quantum mechanics, information cannot be destroyed. It can be scrambled, hidden, spread out, but it must always be recoverable in principle. These two requirements seem contradictory. If information falls into a black hole and is destroyed, quantum mechanics is violated. But if the information somehow escapes or is preserved, general relativity seems to be violated. This is the black hole information paradox, and it's been one of the central problems in theoretical physics for 50 years. The resolution seems to involve the holographic principle and Hawking radiation. The information that falls into a black hole isn't destroyed. It's encoded in subtle correlations in the Hawking radiation that the black hole emits. The process is incredibly complex. It would take longer than the age of the universe to decode the information from the radiation, but in principle, it's there. The information is preserved, but in a highly scrambled form. This suggests that black holes are the ultimate information processors, scrambling information in the most thorough way possible while still preserving it. And the time dilation near black holes is part of this information processing. As information approaches the event horizon, time slows down from an outside perspective, effectively freezing the information at the boundary. From the inside perspective, the information falls through and is scrambled. Both views are correct, describing the same reality from different perspectives. But here's the truly mind-blowing implication. If this is how black holes work, it might be how the entire universe works. The universe might be a vast information processing system, and what we experience as space, time, matter, and energy might all be emergent phenomena arising from this underlying information dynamics. In this view, asking, why does gravity slow down time, is like asking, why do waves in water make things bob up and down? Question assumes that water and waves are separate things, but really, waves are patterns in water. Similarly, gravity and time might not be separate things. They might be different aspects of the same underlying information theoretic structure. This brings us to one of the deepest questions in physics. What is spacetime made of? Is it fundamental and continuous, infinitely divisible like a smooth fabric? Or is it made of discrete units, quantum pixels of space and time? This question is at the heart of attempts to create a quantum theory of gravity. The leading candidate is string theory, which proposes that fundamental particles aren't point-like, but are tiny vibrating strings. Different vibration patterns correspond to different particles, and one of these vibration patterns corresponds to the graviton, the hypothetical quantum particle of gravity. In string theory, gravity is unified with the other forces, and spacetime emerges from the dynamics of strings in higher dimensional spaces. But string theory is controversial. It makes few testable predictions, and it requires extra dimensions beyond the 3 of space and 1 of time that we experience. These extra dimensions are supposedly curled up at incredibly tiny scales, too small to detect. Critics argue that string theory is more mathematics than physics, beautiful but untestable. An alternative approach is loop quantum gravity, which takes spacetime itself as fundamental and applies quantum mechanics directly to it. In this theory, space is made of discrete loops, and time is made of discrete steps quantum pixels of spacetime. The smooth spacetime of general relativity emerges as an average over these quantum fluctuations, the same way a smooth water surface emerges from countless water molecules. Loop quantum gravity makes different predictions than string theory, including the possibility that the Big Bang wasn't actually the beginning of time, but rather a quantum bounce from a previous contracting phase. Time might be eternal, cycling through expansions and contractions, with our universe being just one phase in an endless process. Which theory is correct? We don't know. We might not know for decades. The energies required to test these theories directly are far beyond anything we can create in particle accelerators. But indirect tests are possible. Gravitational waves, black holes, the cosmic microwave background radiation, all of these might carry subtle signatures of quantum gravity that we can detect with sufficiently sensitive instruments. Here's your 4th retention hook. I've told you how gravity slows down time, how this connects to information and entropy, and how it might emerge from deeper quantum processes. But the most personally relevant question remains: how should this knowledge change how you live? If time is relative, if the flow of time is an illusion, if all moments exist eternally in the block universe, what does that mean for how you should think about your life, your choices, your mortality? The answer is both liberating and terrifying, and I'll reveal it soon. But first, we need to explore one more piece of the puzzle: the cosmological implications of gravitational time dilation and what it means for the fate of the universe itself. Now let's expand our perspective to the entire universe and explore how gravitational time dilation affects cosmology, the study of the universe's origin, structure, and ultimate fate. Because when you apply these principles at the largest scales, you discover something astonishing. The universe itself is a time machine, and you're traveling through it right now. Here's what I mean. The universe is expanding. Every galaxy is moving away from every other galaxy. The farther away a galaxy is, the faster it's receding. This was discovered by Edwin Hubble in 1929, and it revolutionized our understanding of the cosmos. But here's what's less widely known. Because of relativity, this expansion creates time dilation on a cosmic scale. Imagine 2 galaxies separated by 1 billion light years. Due to the expansion of space, they're receding from each other at a significant fraction of the speed of light. And when objects move relative to each other at such speeds, time dilation becomes significant. An observer in one galaxy would see time running slower in the other galaxy. And the farther apart the galaxies, the greater the effect. But here's where it gets truly strange. The expansion of the universe isn't just galaxies moving through space. It's space itself expanding. New space is being created between galaxies. And this expansion has its own effect on time. In an expanding universe, clocks at different cosmic locations tick at different rates, not because they're in different gravitational fields, though they are, but because the expansion itself affects the flow of time. This is described by the Friedmann equations, derived by Alexander Friedmann in 1922 from Einstein's general relativity. These equations show that in an expanding universe, there's a natural cosmic time